All right, good morning, everyone. Just a rundown of a few things to keep in mind. Exam, of course, is a week from today in the evening. But coming up, then there's going to be some review going on. You already are able to review those old exams in the back of your workbook. There's a nice listing of which problems you should be able to do. I'd take that listing and cross out or circle the ones you can do, just so you know that there's some you should skip on the final exam, of course, and there are some that you should do on that old exam 1. Might need to review that binomial test, because that is still a hypothesis test about a proportion and could be asked also next Thursday. If you haven't looked at yet, I know some have, those bright yellow sheets that are in the back of your workbook. Some of these are going to be very helpful for reviewing for the exam. There are supplements that were put up front on bright color, so you might pay attention to them or take a look at them. And it's supplement number 5, 6, and 7. Those will be the good ones to focus on. And perhaps a little bit of number 2, which is just a notation worksheet. But supplements 5, 6, and 7 are looking at the t-tests, which were the newer material since exam 1 for sure. We're going to have some nice summaries, some nice interpretations, and a little clarification of when do you do 1 minus on that p-value when you cut things in half. So take a look at those perhaps. And then next Tuesday and Thursday for us, we'll do a little bit of lecture review along with some new. I've got to look at those questions one more time before I put them up, but they'll go up probably tomorrow. And I'll ask you to bring them for class next Tuesday and Thursday. Pre-Lab 8 is already open. That's on ANOVA, Analysis of Variance, that we're doing right now. So you could complete that at any time. And of course, you should know where to go for your exam. Same place as exam 1. Review will be next Tuesday. We have MLB Odd 3 next Tuesday evening. Questions will go up by tomorrow for you to have over the weekend. Captured that night and put up later that night or Wednesday morning latest, if you aren't able to attend. Questions or comments at all before we do our ANOVA today? Anything? Nothing. Okay. We're doing something called ANOVA, Analysis of Variance. This summary on your page 174, I believe, is what appears on your yellow card under that section. This is at the bottom of that second page of your formulas. You will not need to use this information next Thursday night. ANOVA will be on the final exam. But analysis of variance is really an extension of the 2-sample pool t-test. It is still working with a quantitative response. We're still going to be comparing means. Your homework 7 is all about comparing 2 means, mu1 and mu2. Making sure you can distinguish that scenario from the one where the 2 sets of data are really paired. When you have more than 2 groups, we need another technique. Analysis of variance could be used. I mean, you could actually do ANOVA if you wanted to, do it to that 2-sample problem that might be on the exam, as long as it was comparing those 2 means as being equal or not equal. Because that's exactly the test that ANOVA F-test is doing. Are the 2 means equal? Is at least one different? That means they're not equal. So really, turns out that you would have calculated a t-statistic, and perhaps you pulled that out of the output on your homework. And if you would have taken that t-statistic from a pooled t-test and squared it, it would turn out to be equal to the F. The statistics would be the same. If you did an analysis of variance with 2 groups, which you know you could do the pool technique for those same 4 conditions that are holding, the F statistic that you would compute in ANOVA would end up being the square of your t. Now, does that make sense when you look at the distributions of those statistics? What does a t-distribution look like? Symmetric, centered at 0. What if you were to square all the values? Then none of those negatives would be there. They would go over and move to the positive. And you would have a skewed to the right distribution, which would be the F distribution. So there is this unique relationship. Now, obviously, when you go to more than 2 groups, then we have to go to the analysis of variance technique to first compare the 3 simultaneously and then look for differences, which is what we'll be doing today. So we did a lot of work last time in getting our F statistic and putting it there in that analysis of variance table that lays out the different pieces that lead to that F statistic. The F statistic was formed from this ratio of 2 mean squares, 2 variance estimates that came from our data. One that was good and one that was only good if H naught's true. So it allowed us to compare them to help us decide if we stay with H naught or not. All right, we worked with some data, 19 subjects in all. Next page was the data set we started working with. Trying to determine whether or not these 3 different drugs are equally effective in terms of their population mean response to treatment. How quickly did they feel better? We tested the hypotheses, or that's what we want to do. We want to test the hypotheses of mu1, mu2, and mu3 being the same, no difference between the 3 drugs on average, versus at least one of those population means is different. And then we proceeded to use the data to go through those 6 steps to get our full ANOVA table put together. So the next couple of pages highlight those steps we went through. We talked about maybe on a homework you might have to do some of these steps in detail. On an exam, often some of the steps, at least steps 1, would be completed for you, if not a couple of the others. But we ended up getting this F statistic of 4.2, and your ANOVA table from SPSS is shown on page 177. We filled in the one at the top, and then we saw, oh, look, there's SPSS. It does it for you, including that nice information that's in that last column. So we don't have to try to look it up from a table. So now we have a few questions that would typically come along if you're doing an analysis of variance. We often would want to have some estimate of that common standard deviation that we would use to do a confidence interval later. Because every confidence interval needs a few standard errors, and that standard error needs that estimate of that standard deviation in it. So what would I use from my analysis that I've done here for an estimate of the common population standard deviation? Well, the F statistic, if we remember, is that ratio of those 2 mean squares. And those 2 mean squares are both estimating the common population variance. One of them was the good one, always good unbiased, as a general estimator. And the other one was only good if H naught's true. And otherwise, it tended to be way too big, tend to overestimate. Do you remember which one was the good one, the top or the bottom? It's the one on the bottom. The bottom one is your better estimate of the standard or variance, mean square for within. So would I use then 2.624 here as my estimate of the common population standard deviation? What do I need to do yet? One more step. I want an estimate of the standard deviation, not the variance. We did all this work to get 2 estimates of the variance, these mean squares, and therefore I need the square root. Square root of 2.6 is about 1.62. Your yellow card refers to the mean square for error as SP squared. Mean square for error between the groups. And therefore, this really is SP. It's the same SP you did when you had 2 groups, now just extended to having more than 2 groups. It is the right pooling of those S squareds, and then you take the square root at the end. So there's our standard deviation. We'll be using that later today to make a confidence interval for the drug that we think ends up being the better drug as a whole. Now, if the table is already conducted and provided for us, we will just have to give the observed test statistic value, just report it. And our F statistic value is 4.188 or 4.2 when we round it a little bit in our calculations. You might be asked to talk about what distribution does it have. The question that comes next says, what distribution does our test statistic have if the 3 drugs are equally effective in terms of the mean response? What's this long if at the end really saying? What's the shorthand version of that? If H naught is true. If H naught's true, what's the distribution of your test statistic? We've asked that question in other homeworks and such. Every test statistic has a distribution that it would follow if the H naught is true. And that's the distribution used to find the p-value. That's the distribution used to draw, to shade in the p-value. So this is an F statistic. So what distribution does it have if H naught's true? Some type of F distribution. There's a big clue for this answer in your yellow card directly. Page 174, showing that yellow card summary. Bottom right corner, under H naught. The F statistic follows an F distribution. Now it puts in those generic degrees of freedom there for you, but where can I find that k minus 1 and n minus k already in my ANOVA table? It would be what 2 numbers? 2 and 16. Those are the 2 associated degrees of freedom that were used in making that F statistic for the numerator and denominator. So there's that distribution that we would end up using. I might ask you to sketch it. What would a sketch of the p-value here look like? To draw a p-value picture, you need to have your test statistic, F, and its model or distribution drawn. So I just draw somewhat of a skewed distribution to the right. With only 2 degrees of freedom in the numerator, it actually would be sort of asymptotic coming down. It wouldn't start out at that 0, but that's okay. Just drawing a skewed right distribution is the general picture. And we would put on that distribution the value that we observed, which is 4.188. Because the p-value is the probability, assuming H naught's true, that you would get your test statistic value, 4.188, or something more extreme than that. You're sort of measuring how likely it is to see what you got through your test statistic, or something even more supporting HA. And as extreme or more extreme for an F test is always the area to the right. Because your F statistic was set up to have that top quantity, that mean square for the groups, ended up being too big if H naught's not true, tended to overestimate. So the only direction of extreme was to the right, to the larger values. So what is that corresponding p-value that we just shaded to represent it? Our p-value turns out to be equal to 0.34. That sig there, the observed significance through your p-value, is right there. You don't have to divide it in half or do a 1 minus. That is your area to the right. So we need, of course, our decision and then a conclusion. So I've got 4 options that you can pick with your clicker next. You should be able to weed out 2 of them right away, because that universal rule needs to be known well for your exam next week. And then I'm going to say there's also 1 improvement we can make even on the correct answer that we will be picking here. So your p-values, 0.034. If there really was no difference between the 3 drugs, we would see the test statistic we got are more extreme, larger, about 3.4% of the time if we did this over and over. Not very often. So which of these would be the appropriate combination of a decision and conclusion? What happened here? I don't want that open. Sorry. All right, we should be able to weed out 2 of them because we know what the decision is. And then, of course, there's the 2 different possibilities. Look back at what H naught is, what HA is. What's the rule again? If your p-value is small, you reject the null. All right, let's see how we're doing. Most are picking the correct choice, which would be B. We would reject H naught. H naught was equality of the means. At least one of the three drugs appears to be different. That's what HA says. Now, how could I improve on that conclusion maybe one step further to make it a little clearer that it's the conclusion about the populations? At least one of the three drugs appears to be different in terms of the population average response, or the average response for the populations that our samples represent. Because we are really making a conclusion about those population means, because we already know the sample means we're different. All right, it should be B. So if at least one of the three drugs seems to be different in terms of that population mean response to the drug, should we just stop there? We did our test. Of course, wouldn't you want to know which drug really is the different one? Or are they all three different from each other? We saw descriptively that drug 3 looked the best. Is that the one that's the winner over the other two? So we want to do a little more follow-up. If we reject H naught in your first basic ANOVA test, then our next step would be to make some comparisons. All right, is it drug 1 and drug 2? Were they the ones that were different? Is it drug 2 and 3 or 1 and 3? Those would be the three different pairwise comparisons we'd want to do. And we know how to compare two groups. You're doing it on your homework 7. One of your homework 7 questions says make the confidence interval for the difference in your two population means and see if zero's in there or not, to see if there's a difference. Or you have been doing some formal testing where you calculate a t-statistic and look at that p-value to see whether or not those two means were the same or different in terms of the average commuting time for your two routes. So we want to do some kind of comparisons like that, but I need to do it 3 times to be able to look at all those different combinations. And what I want to be careful about is that my overall level of confidence across those 3 intervals I make can still be 95% as a whole, or that my chance of making a type 1 error before I look will still be no more than 5% across that collection of tests. So to be able to control for that, to make sure that the type 1 error rate stays no more than 5% or the confidence level maintains 95% or higher, we have to have some other techniques. Because right now, if you were to do 3 separate confidence intervals, each 95% confidence, the overall confidence won't be 95%. What if I talk about those intervals before I look, so I can talk about probability? The probability that the first interval, I haven't looked yet, will contain the true parameter will be 95%. The probability that the next one will, when I haven't looked yet, 95%. Third one, 95%. What if you want to talk about all 3 of them being good? What's the probability of this happening and this and that last event? When there's ands, if they were independent, you could do what? Multiply. Multiply 0.95 times 0.95 times 0.95, and it starts getting smaller and smaller. So you start losing that confidence level. So we need a technique, and there's quite a few different techniques that allow us to do this, depending on whether you're just doing pairwise comparisons or other comparisons too. There is Tukey's, Bonferroni. I could list a whole bunch of them. And when you pull up the menu for doing multiple comparisons in SPSS, you have to pick one. And the one that we're going to do that's basically a reasonable one, not too conservative, handles the pairwise comparisons that we will want to do, is called Tukey's method. It basically sort of takes your alpha, and if you're doing 3 comparisons, it does alpha over 3 as your level alpha for each of those to put them together to some extent. But here's the idea. We're going to do Tukey's. We're going to do it with SPSS only, so you're going to get output that looks something like the bottom of your page there. This is your standard multiple comparisons output using, up in the corner there it says Tukey's, for looking for significant differences. So which drugs were different? We have 6 rows of information because it did 1 versus 2, that difference, drug 1 minus drug 2, and it also did 2 minus 1, which of course is really the same information, That's why some of you might get an interval around a negative 3.6 versus a positive 3.6 when you make your interval. One of your questions, they're both right. It's just a matter of how you defined 1 and 2. All right, so we have at the end of our output here the confidence intervals, and that's what we're going to be using to see whether we have differences somewhere happening. Which of these intervals either have 0 or don't. So let's take a look. We first want to compare the first two drugs, drugs 1 and drugs 2. mu1 minus mu2. Did that confidence interval for that difference contain 0? So here's the interval for 1 minus 2. And that interval goes from negative 3 to plus 1. So does it have 0 in it? Yes. If there is 0 in the interval, then mu1 minus mu2 could be 0. You'd have to accept that. You could not refute it. Which means there is a difference or there's no difference. If 0 is in the interval, that means those two population means could be the same. No difference. All right, so that's not where we ended up rejecting H0 for. How about the first drug and the third drug? That's the next one right in our list. Goes from a negative 1 to a plus 3. And that, of course, has 0 in it, too. Well, we got one more possibility here, and we're looking now at drug 2 versus drug 3 for comparison. Those happen to have been the two drugs that gave us the most difference in the sample means. Drug 3 was the best, drug 2 was the worst. So that is the largest difference descriptively. And if we look at 2 versus 3, that confidence interval goes from just a 0.2, but up to then 4.7. It does not have 0 in that interval. There's where there was a significant difference between those two groups that led us to rejecting H0 in our ANOVA F test. Now, in an exam, you might be asked to cite what values are you using up there in that table to make your decision about where the differences occur. So make sure you do talk about those values or circle them or point to them or something. All right, now there is some other clues here. You've got what the actual difference in the sample means was with their corresponding standard error. If the sample sizes were all the same, the standard error would all be the same. All the N1 and N2s would all be the same. Here we had 5, 7, and 7, so there was a little difference. And then here's your sig, which is again your observed significance or p-value for the two-sided t-test if you did the test instead of the confidence interval. So that is the two-sided p-values, and you can see accordingly that the only comparison that has a small enough p-value is the one for drugs 2 and drugs 3, 0.027. So these are the two-sided p-values. Whenever it's doing a t-test in SPSS, it's always going to give you the two-sided one by default. Do you also see another big clue that tells you where the differences were significant at a 5%? It's got a little footer, right? The little asterisks, and it says those are where the differences are going to be significant. Now, I usually take that out at an exam. I remove that footer so the asterisk goes away, so you just find the significant differences accordingly. Right now, though, you could either cite the p-value as your reason why you said it's significantly different for 1 and 2 and 3, or you could use the confidence interval approach. So what should we write up then in Part B? State some conclusions then regarding the differences between our mean responses for our 3 different drug group populations using our Tukey's method. So you've got that the population mean responses appeared to differ which 2 drugs again? It was drug 2 and drug 3. So that's what we want to state up front. It seems to appear to differ for subjects taking drug 2 versus drug 3. But not differ for those other combinations. Not differ for subjects taking drug 1 versus drug 2. There was no difference there, nor for the comparison of drug 1 versus drug 3. kind of strange that if 3 is not different from 1, and 1's not different from 2, well then why isn't 3 not different from 2? But they were the ones that were furthest apart. So they ended up being different. In fact, I'm going to show you one other visual picture that you might see in output. Some of the questions from the textbook use this kind of idea. And that is to take your 3 sample means for your 3 drugs or 3 groups and put them down in order from smallest to largest. So it was drug 3 that was the best descriptively. The lowest sample mean, these are the sample means or the X bars, was 6.8. Then the one in the middle was drug 1 that had an average of 8.22 that we calculated for just those 5 subjects. And then it was drug number 2 that had the highest sample mean. That was 9.3. So those are the 3 sample means. And what technique is to draw a line to connect any pair of drugs, any pair of groups, in which there is not a significant difference. So they basically are on the same line. And we found that drug 3 and drug 1 were not different. So those have to be connected. So let's draw a line that connects those 2. We also found that drug 1 and drug 2 were not different, but that 3 and 2 were. So I can't extend this line straight out because that would put drug 3 and drug 2 on the same line. It's another line that connects the 2 drugs at the end here. And because there is a step or a difference there, that drug 3 does not sit on the same line as drug 2, that's where the difference occurred. So that's just a visual picture. They often will do that with little plotting on many computer packages. What would the picture look like if drug 3 were significantly better than the other 2? So it was better than 1 and it was better than 2. Then this line would be removed, and those 2 might still sit together, but 3 would be not connected to either one. If we had that there was no difference anywhere, if we had stayed with H0 in the first place, there would have been a solid line across all 3. And if every drug was significantly different from any of the others, there was a big enough gap between any pairwise comparison, then there would be no line at all. A couple different possibilities. All right. Now that we have found that drug 3 at least is different and better than drug 2 on average, let's maybe go a little further and talk about drug 3. You could go back to the 1 sample t-test stuff you've done to make a confidence interval, or to further test something about that average response of drug 3. Well, one way to do that, though, is to not go back to the original t-test procedure, but to use all the data still, even though you're going to focus on 1 drug. So the last formula under this ANOVA section is to give you a better confidence interval for a single population mean. Now, it kind of looks the same. You might be asked next Thursday to make a confidence interval for a population mean. 1 set of data, quantitative response, there's the sample mean there, there's the sample standard deviation, and make a confidence interval. So you would take your best guess, X bar, and you would go out plus or minus a few. And what's the thing that goes after that? A few standard errors. And the standard error that we know in general is S over square root of n for a single sample. So that's the formula you have on your yellow card for doing a regular confidence interval. What's changed here is that you've got a little X bar I because it's for whatever group you're talking about. And the sample size down below has to be for that group. But the S that's on top isn't going to be the S just for that 1 group of data, just for group number 3. It's SP. So it puts SP down here, the better pooled standard deviation estimate using all 19 observations from our drug study, rather than just only the 7 subjects that had drug 3 and using that S. That's a better multiplier than that we can gain because we always take degrees of freedom for this based on the S. The degrees of freedom are what is associated with that corresponding standard deviation estimate. And if you remember the degrees of freedom for SP is N1 plus N2 minus 2, or N1 plus N2 plus N3 minus 3, or that N minus K in general, rather than just an N minus 1. So that's what's different in this particular formula. That's on your yellow card to use, so let's apply it to be able to report drug 3 seems to be better than at least drug 2. Give me a nice interval estimate for the average response for drug 3. So let's take a look. You have the summary of your 3 drugs with the 5, 7, and 7 subjects for the sample sizes. Here are those same sample means we just took a look at. We had 3 groups altogether with 19 observations, and one of the first things we calculated today was that 1.62, the square root of that SP squared. The square root of that mean square for error, which is our best estimate. So now we can look up a better multiplier using our full degrees of freedom. Even though we're going to do a confidence interval just for drug 3, which only had 7 people in it, I get to use still 19 minus the 3 groups, or 16 degrees of freedom, instead of just 6. So I can look up that multiplier, which will be a smaller t star, and therefore a more precise interval. So a multiplier when I have 16 degrees of freedom and 95% level of confidence is going to be a 2.12. Instead of being much larger, like almost 2.5, if we had used only 6 degrees of freedom. So that's going to be a better multiplier. So our confidence interval, to be able to describe what kind of values could be possible for the average response for drug 3, would start out with our best guess of 6.8. It would go plus or minus that few, and then we need to put the right standard error. It is an S over square root of n, but the S we're going to use is from the full data set, which could be used to get an overall estimate. And that SP was 1.62. Sample size, though, was a 7. If I multiply this whole part out here, what is this called again? Has a name in general for any confidence interval? Your margin of error. And if you're ever given the margin of error, you don't have to compute all the parts then. But this margin of error here would be about 1.3. And our range of reasonable values for the population mean response for all subjects if they were given drug 3. We would estimate their average time to cure to be from 5.5, maybe 5.5 days, up to 8.1 days, or whatever units we have here. There's the range of reasonable values. All right. There's our confidence interval. Now, what are the common mistakes if you were to do this on an exam for a final? You just put in your right sample mean, but you put in the wrong standard deviation. You put the standard deviation for drug 3. That was maybe calculated and summarized for you, but you used that standard deviation instead of the full SP. So you need SP here, and you need the full degrees of freedom. And often I'll see the wrong T star and SP put in. All right. There's our 3 drugs example in full. We get to do one more full memory ANOVA example together before we finish this material up. I think my pictures of the day are next. They are. These are just some of my favorite family pictures. Isn't she cute? She looks like me, dressed the same. Now she has long hair, not the same. Yeah. Family. So moms like to hear from you guys, especially their boys, that you're okay. We just need to know that every once in a while. So if you haven't texted your mom or emailed her lately, let her know. Girls, same thing. We just like to know everything's okay. Keep in touch with your family. All right. Your son's out skiing out west, and you text him, how's the snow? You don't hear from him for 2 days. You don't. All right. One last full ANOVA. This was from an old exam. Some of the kind of questions that could be asked in an ANOVA problem. I know ANOVA's not on your exam next week, because that exam is almost all done. But still, some of the ideas do extend. All right, we have 3 groups of subjects. They're each given a list of words to remember. Have you ever done that, where you get a list of words and you have so much time to look it over, then you try to recall as many of those words as you can? Well, for this experiment, the 3 different lists were of different lengths. There were only 10 words in the first list. There were 20 words that they were asked to look over and try to memorize in that second group list. And for the third group, their list was long, 40 words. So since the number of words in each list was different, we can't actually just count how many words did they remember. Because in the first group, the most that could be is 10. And in the last group, someone could remember 32. So that would not put it on the same scale. So instead, the response here is actually the percent of words that that person recalled, which is still quantitative. When this was on an exam, I had some students trying to do proportions instead of means, even though it's ANOVA and that's about means, because the percentage was in there. But what we're recording on each person is what percent did you recall. You had the short list, you remembered 8 out of 10, you're 80%. 80. Someone had the long list and they remembered only 20 out of 40. Their answer, then their recording value is 50 for 50%. So now it's on the same scale, 0 to 100%. All right, so that's what the data would look like. I don't need to give you the data for all the subjects, but I am going to summarize their sample means for you. The average percent of words recalled for those subjects in the short group was 68%. The average percent of words that could be recalled for those that had the medium length list, not quite half, and it keeps going down, as you might expect. They could only recall about 39% of the words on average in the long list group. So those are the sample means, the X bar 1, the X bar 2, the X bar 3. It tells you we're doing one-way ANOVA. It's not that big of a clue there because you got the ANOVA table sitting there too. But we're trying to use ANOVA then to see whether the length of the list had any effect on this response in terms of the average response. So if we have 2 variables here, the percent of words recalled is one of them, and the length of the list is the other. Which one's the response? Which one's explanatory? The percent of words recalled is your response variable. The outcome of interest, that is quantitative. And the length of the list would be your explanatory variable, if you had to identify those from that idea of design of studies. All right, so we're asked to complete the ANOVA table. It's not quite complete, but it's not hard to complete it. We're given 2 out of the 3 sums of squares. We don't even need the formula card to calculate this sums of squares within the groups. In fact, we don't have the raw data enough to do that. But we can get it by subtraction, because we're given the total and the sums of squares between. So by subtraction, we would have 1,184.1. You also could get the degrees of freedom by subtraction. I could, however, also take out that 2, and you could still complete the table. As long as you had the 16 there, you could still do it. The 2 comes from what? How many groups are we comparing again? 3. So 3 minus 1, k minus 1 degrees of freedom for the groups. That would be easy to do. But you could not compute this first if both of those were missing, because you need to have the n. And you can get the n through the 16 too. But what is left over? We have 2 here, we have 16 here, we have 14. How many people were in this study then? How many subjects were in this experiment? Tell me. Didn't say anything in the paragraph how many were randomly assigned to the different groups, but how many must have been in it? Yeah, 17. 17 comes from the 16, which is your n minus 1. Also would make sense to have 17, because 17 people minus 3 groups give me that 14 degrees of freedom too, right? So this 16 here does tell me that there were 17 subjects altogether. I think that was one of the questions before. How many subjects must have been involved in the study? 17. So it wasn't quite a balanced design. You can't divide 17 up by 3. Perhaps it was 6, 6, and and 5. What are the classic hypotheses we test with this F statistic we're going to calculate here? Let's see, we still need our mean square for between. So cut that 2,000 in half and get our mean square for between the groups. 1,300 over 84 will be this F statistic that we use to test our hypotheses. And that F statistic is 15.77. That's even bigger than our last F statistic, 4.2. And that p-value sitting next to it is even smaller, because we are even further out in an F distribution tail. The hypothesis that that F statistic is testing is what? What's wrong with this? I'm not testing that the sample means are equal. The sample means were reported right there and they're not equal. I know that. Nothing about the sample goes in H0 or HA. You don't look at the sample results and see that one of those routes was better than the other and change your alternative to show that or test that. You test what you initially were planning to test, which is in ANOVA, are the 3 population mean percent of words recalled the same? In other words, the length of the list didn't have any effect, versus what for HA again? That's the one we have to write out in words a little bit. At least one of those population means is different. I don't know if I have you click in for C or for D. I can't remember. But let's keep going. Stating the hypotheses. These are not on your yellow card, but make sure you clearly state your hypotheses about the populations. In your hypotheses next Thursday night, they should be having values like mu1 and mu2, or p1 and p2 for 2 proportions, or a p, not a p hat, a p for a population proportion. And if you're doing a test about a population proportion and your sample size is only 5, you've got to do what kind of test? Small sample binomial test. Or perhaps if it is a pair design, I know I don't want to put down there mu1 and mu2. In a pair design, you should put down mu d, because that's the parameter of interest. You're hypothesizing about what the average difference would be in a pair design. All right. Oh, I think I skipped. No, is that right? That's our next question, isn't it? Using a 5% level. Does it appear that the population average percent of words recalled is the same?
I think you didn't start it.
I didn't start it. Okay. That would help. There. Thank you. You do have to be able to do some testing next Thursday night and use the same universal rule every time. If you are done with your clicking in of your choice here, go ahead and look at Part D. Figure out which ones you're going to circle. Give you another minute to look at that too. So try Part D out also. This is that multiple comparisons. Figure out which ones you're going to circle to answer your question. And check that one with your neighbor. right. For this ANOVA test, at a 5% level, we're supposed to assess whether we say yes or no to this question. Do you know what decision you would make? 5% level, and your p-value is really, really small. So you will do what? You will reject H0. What does reject H0 mean in terms of saying yes or no here? Majority do have it correct. Our answer here should be no. Does it appear that the population average percent of words recalled is the same? Does it appear that you should stay with H0? Because that says they're the same. And we'd say no, you shouldn't stay with H0. You should reject H0. Since the p-value is small, much less than or equal to 0.05, which is our level of significance, or alpha, we know that we'd reject H0. H0 is that the population means we're all the same. We just wrote that out in Part A, or Part B. So if we're rejecting that H0, then our answer is no. Does it seem like they are the same? We would refute that. We would reject that. All right. If the question had said, at a 5% level, does it appear that there's no effect of the length of the list on the average percent of words recalled, we would say, what? Does it appear like there's no effect? No, there is some effect. All right. Since there is some effect based on our data, since it looks like at least one of those population means are different, then multiple comparisons is one way to decide where did that difference occur. What you have here are only the confidence intervals and the little asterisks telling you which ones are significant removed, so you will find them. So I know that I need to do what? Look at these confidence intervals and start to find the confidence intervals that either do have 0 or don't have 0 in them. I'm asked to circle the pairs that show there's a difference. So that means I want to find the confidence intervals which what? Do have 0 in them or do not. If I want to show differences, then I don't want 0 in the interval. So looking at the intervals, which ones do not have 0 in it? That very first one doesn't. Is there a difference between the short and the medium list? Yes. So short and medium I should circle. Is there a difference between short and long? Well, does it make sense if there's a difference between short and medium? Short and long would also be significant. And it is. Medium to long, when you make that jump, there's a 0 in there. So I do not circle that pair. So we're not circling the pairs for which we find the 0. We're circling the pairs where there's a difference, meaning that there was no 0 in that confidence interval. All right, and it's possible that you might circle only 1, 2 of them, or possibly all 3. But at least one of them, if indeed you rejected H0. All right, so we're asked to wrap up with a confidence interval for the percent of words recalled for those that were in the long list group, that third group. The sample mean was reported to us up in the summary at the top. 39.2% of the words were recalled on average for the long list group. So that's our sample mean, X bar. We want to do the confidence interval at a 99% level. The formula on our yellow card says use the particular X bar for that group. Go up plus or minus a T star. And then it's got SP over the square root of N sub I. That's what it looks like. So the sample mean for that third group, the group with the long list, was 39.2. I'll need to look up a T star in a moment. But how about this standard error? The sample size, it told us that there were 6 subjects in that group. So remember, all we knew right now that there was 17 subjects altogether. We didn't have the individual sample sizes given to us. But now it did report that there were 6 people in that group. And how do I get SP? What information do I have that allows me to get that? That's your estimate of the common standard deviation for the populations. And you've got 2 mean squares sitting up there in that ANOVA table that are both estimates of the common population variance. Which one should we use? Regardless of whether we rejected H0 or stayed with H0, if we did in our F-test, we should always use the one that is an unbiased estimator in general, because we don't know if H0 is ever true or not. And that would be the one on the bottom, the error on the bottom. Do I put in 84.6? What do I need to do? Square root of that. SP will be the square root of your mean square for error, or within. The square root of the 84.6 needs to be found and put in there. And then how do I look up T star? Common mistake. Look up T star with 5 degrees of freedom, because there were 6 subjects. But because I'm using SP, which is based on the full, how many degrees of freedom? 14, because that's the degrees of freedom that led to that better estimate. I need to use 14 degrees of freedom. And using 14 degrees of freedom with a 99% level of confidence, and just making sure I'm staying in the right row and column. 99% gives me 2.98. Want to be a little more confident, you got to go a little bit further out. 2.98. Now I've got all the numbers plugged in. This is what I would look for the minimum of giving you credit. Okay, that everything's plugged in correctly. So I have a final answer with no work behind it. You don't get points. If you have a final answer and work behind it was correct, but your answer's off a little bit, maybe you just multiplied or forgot the square root, so I at most 1 off. Can give you some partial credit. The plus or minus part, the margin of error, about 11/19. So my bounds for my interval, I would estimate that percentage of words recalled on average for subjects getting that long list to be anywhere from 28% all the way up to a little over half. I would have to support that there could potentially be a majority of words recalled, even though in the sample there were not. It did extend past 50%. That's just one of the intervals. I could have you do it for any one of those 3, usually on an exam just once. Good full ANOVA problem to follow along with on homework 8, going up next week after the exam. You take a look at it. One last page, please. Page 181. You do have to know your conditions. You have to be able to state them or perhaps be able to assess them, where we give you information to be able to do that. In ANOVA, the 4 conditions are the same for your 2-sample pooled t-test or confidence interval. You have to assume that your samples are each a random sample, right? That those samples are independent by the design of the study typically. You have to assume that for each population, if you looked at the model that described your response, your percentage of words recalled, the model for that response in each population would be normal. And then you also have to assume that equal population variance. Sometimes normality isn't met. And if I only had 17 subjects altogether, 6, 6, and 5, and my QQ plots looked quite off, well, then I'm stuck because I can't even rely on what famous result to help me out here? The central limit theorem. Central limit theorem requires what kind of sample sizes sort of as a minimum? 25 to 30 and up, you're going to be okay? I don't have that at all. So if that's the case, if you have data that's really skewed, there's extreme outliers, we really have to turn to not the mean as your thing you're trying to learn about, but the median. You're going to want to just know these by name. I'm not going to teach you how to do these tests. You can, pull down the menu and have SPSS run them for you. There are tests for comparing the medians instead of the means, which do not require that the populations have a normal model. It's a non-parametric test because there's not a parametric form that's assumed for the model. for your population. Doesn't assume it's normal or some particular type of distribution. It just has some density is all. So those are tests that are a little less powerful, but at least they could be done if you don't have the assumptions met. They would have p-values, and you could still take p-values and know how to make the decision, but it would be talking about then the medians instead of the means. There's also a median test called mood medians test. So these tests are available. When we complete at the end of the course the full grid of all the different techniques you used, and sort of in a structure so you know which ones to use. We're starting to do that already with our 5. We'll put these in there by name, but you won't be asked to do them, of course. And then, last idea before you go. We did one-way ANOVA. Maybe you'll be asked to identify the explanatory variable in the response. You could be asked that even in a 2-sample problem. Teaching method is the explanatory, the response is test scores being compared. When you want to look at more than one factor affecting that response, give me about 2 more minutes, please. More than one factor would be such as the teaching method and the teacher teaching with it. There could be interaction. One teacher might be really good with one particular method, the other with the other. So whenever you have more than one factor that could influence your response, you've got to analyze them together and look at possibilities of interaction. Is it synergistic or is it inhibitory? We aren't going to be able to go through that technique. That's 2-way ANOVA or multiple factor ANOVA. But if you were interested in taking another stat class, 401 would be the next one to do that. Take 250 one step further, do more data analysis, or maybe think about next winter term, really cool class, honors version of a 100. You keep a journal. You read some really cool articles. I helped develop that material in that class. It's a lot of fun. That's it.